Venkat's talk too. And so yeah, Venkat is amazing. So happy to have Venkat here finally. Yeah, and also this time I'm actually in town. So last time I wasn't in town. So yeah, so really happy to have Venkat here. And thank you again for making this special trip out here, especially if you're at GoTo and you also come over here. So thank you very much. And this is also being recorded too. So, and also too, we also, not just for CJUG, we also have the Chicago Kotlin Users Group, John Burns and Amanda Hinchman, right? Yeah, that's your last name. Yeah. Okay. Yeah. So yeah, I have the two of them here too. So yeah, very, very nice. Yeah. Oh, I should have actually, I didn't even remember to add. I'm sorry. I was in such a hurry today. It's, I got this update. Yeah. Cool. Yeah. All right. Would you like to say a few words too before I start this housekeeping thing? Yeah. So. Okay. Yeah. Okay.
I just
Yeah.
stand up here in solidarity.
Yeah. Thank you.
Coming.
Thank you. Yeah.
We like to talk about Java and Kotlin and all related things, and so we'll have more events coming soon. So
yeah, that's right.
Yeah.
I mean, Amanda too.
Yeah, we've historically done some crossover events, so I don't know if folks in the Kotlin user group before a crossover event. Oh, lovely. Grade 6 and 9 heads. Yeah, and we'll be looking to do more in the upcoming years, so definitely subscribe to like the Kotlin user group channel as well. We'll do our best to like cross post things as well so everyone gets the same messaging. But yeah, it's really great to be able to have like crossovers.
Yeah.
Community, building community.
Right. So, yeah, that's right. Thank you. Yeah, thank you. Thank you. Okay, cool. So I'm gonna just start again. This is more housekeeping thing, and before we have Venkat start. Okay, but first of all, most importantly, if you are interested in JetBrains licenses, they are giving us like donating or giving it to us for free, like complimentary licenses, 2 per month. So if you're interested in this drawing, we're going to do it after the talk and after Q&A too. So this is the QR code and also the bit.ly link. In case you miss it, I can share with you our slide deck too. Then you can also have access to this. So, okay. All right, good. Yeah, all right. And also just a note too, if you won a license within the last 9 months, then you are not eligible because this way we let more people have the chance of winning too. So. Okay, and some housekeeping, if you are not already signed up with the Chicago Tech Slack, our local tech Slack, please consider signing up for that. And then there's also the Java Off Heap, the podcast by Freddie Gimay and Bob Pollin. And Freddie was the previous CJUG president. And then with Bob too, and Bob's still helping too. And then if you haven't joined us yet on meetup.com, this is how you can join us, the Chicago JUG site. So, oops, a little too fast. And please follow us on X or Twitter if you haven't already done so, if you like. And then also we have a Discord server too, if you're interested in joining our Discord server. And then today too, we created, every time we try to create a room, so then we can have specific conversations around that meetup event. So if Venkat, you'd like to join that too, our Discord server, this is how you can join. But again, I'll share with you this slide deck, so you don't need to copy it now. And some community info. We are a community partner with JetBrains as well as devitjobs.us. They have jobs listed throughout the world too for that second website. And just a note too, on November 7th, Neo4j is going to run a virtual developer conference, 24-hour free one. So if you're interested in joining, actually you have to get this. When you click on the Nodes 24, that's the the site of their conference. So I'll share with you this link so then you can get to this slide deck, then you can click on the link to get to that Neo4j conference. And some upcoming events. On November 19th, we're going to have our Neo4j. Neo4j is our gold sponsor, so they're sending Jennifer Reef, who is the developer advocate. She will be here from St. Louis area doing a talk. And we also have a short talk by Dmitry Choiko from Bellsoft as well. And then we have other confirmed speakers, although we're still trying to find the date. Is Oracle, from Oracle is Grauviam, Alina Yurenko. She's based in Switzerland now, and she's originally from Ukraine. And then Josie Pomalt from Oracle, based in Paris. So we're trying to schedule them probably in 2025. And then we're still kind of thinking of doing a meetup too. So if you're interested, please let us know. And if you're interested in speaking at CJUG, please send your proposals to present@cjug.org. And then for job seekers and recruiters, please visit and join our CJUG group on LinkedIn. And that's where we encourage our recruiters to also sign up there and post their jobs there too. Okay, so that's that. And then just wanted to, again, to thank our new gold sponsors, kind of somewhat new. They just came on board back in August, and Neo4j. And then they also actually have a community contest every month too. So they're giving out a free drone. So if you want to enter this into this raffle, please feel free to scan the QR code, or there's also a link in here too. Again, I'll share this slide deck with you, then you can get to it and enter the drone. And I believe Tuan, is Tuan here today? Yeah, Tuan, that's what I thought. I heard too from Neo4j, Tuan won the drone from last month. So it is real, they are going to do their drawing, at their headquarters, but you have a good chance to win too. So please consider entering that raffle. And also today to our venue hosts, thank you again to David Giard. Yeah, thank you. David is our representative contact at Microsoft, and he's the one that helps us to get this venue. So thank you very much. Yeah, thank you. So really beautiful place. Thank you. And I don't know why this is like that, but anyway, just friends of CJUG just want to mention. So they are still, they're running some of these meetups online too. So we are friends with all of the Java community all throughout the world, but these are the ones that are really good best friends and the kind of bestest of best friends at Atlanta JUG, Boston Java user ACM chapter, the Garden State JUG from New Jersey, Kansas City JUG, New York Java SIG, the oldest JUG in the US, and then Pittsburgh JUG too. Okay, and now, and again, sorry why this kind of became like that, but now, without actually have to introduce him, we all know is Dr. Venkat Subramaniam is our special guest today, and he's the world's best living legends in, in software computing. So happy to have you again. And you inspired developers from all corners of the world, Asia, Europe, I see you everywhere, Europe and where else? Europe and I think Africa too, right? You go to Morocco, so in US, and he's a highly sought after speaker and trainer in both academic and business worlds. You're a true polyglot programmer with deep expertise in many languages, award-winning author and co-author of multiple publications and books, and you're contagious and passionate for software development. I got it from your website. This is a good one to mention. You're a founder of Agile Developer, Inc., and you are an instructional professor at the University of Houston. So with that, the stage is all Venkat's tonight. So welcome, Venkat.
Thank you, Mary.
Thank you. Yeah,
Thank you.
Okay. Yep. Do you need, you have
Yeah,
your...
I've got this. Okay, great. Excellent. Well, thank you so much, Mary. I really appreciate it. Thanks so much for everyone who took the time to join. I want to talk about this emerging concept of virtual threads and how we can benefit from that. And the best time to ask questions or make comments is anytime you have a question or a comment. Don't hesitate to ask any questions along the way. It's not an interruption at all. Any questions or comments you have is most welcome anytime throughout. I want to talk a little bit about the state of the world of programming in multi-threads. We'll then dive in and talk about what does it really mean to program asynchronously. Then we'll talk a bit about what threads do, and then we'll talk about virtual threads. I will jump a little bit and talk about how Kotlin does things, and then we'll compare a little bit about what Kotlin does to what Java does and what are some of the differences. And then we'll come back to Java and talk about a few things in virtual threads. We'll talk about some do's and don'ts, and then we'll wrap it up at that point. So let's get started. But as I'm speaking, this is a topic of concurrency. So to emphasize the topic, You don't have to listen. You can get pizza while you're listening. That's a great way to practice concurrency. So as you are listening, you want to grab more pizza, feel free to do so. If you want some drinks in the back, you can do that too if you want to use the facilities. So don't hesitate. We don't have to do things sequentially. Speaking of which, let's talk about parallel, concurrent, and asynchronous programming. So this is a topic which is very confusing for a lot of us. And we often wonder, what does it really mean to be parallel? We talk about what does it mean to be concurrent? And what's the difference between the two? Is something we keep thinking, right? Well, I just demoed it, actually, in case you just did not notice it. I demoed parallel versus concurrent. And I can walk and talk in parallel. I don't have to stop walking to say a few words. I don't have to pause saying a few words to take a few steps. So I'm able to talk and walk in parallel. So when it comes to a parallel operation, we can think about it like so. And here is, let's say, a timeline we are looking at. And during this timeline, it turns out I can talk during this timeline, and I can at the same time walk during the same timeline as well. So it turns out I can actually talk and walk in parallel. However, as you may have noticed, it is rather very dangerous health-wise and definitely very impolite for me to talk and take a sip of water at the same time. You're probably going to kick me out if I try to do it. So I cannot talk and drink water in parallel. That's not going to work. So while I'm talking, I might actually drink water. And then I may continue to talk a little bit. I may take a few more sips. And then I may talk a little bit. And I may take a few more sips and drink as well. So as it turns out, I cannot talk and drink in parallel. I shouldn't even try. But I can talk and drink concurrently. But why is it concurrent? Well, the reason is I don't have to speak for an hour and then take a pause for 15 minutes while you all watch me sit and drink this cup of liquid to empty it. And you're like, what is he doing? Oh, don't bother. He's drinking water right now. And it's going to continue for the next 15 minutes. Well, that's not the way we normally do things. As I'm speaking, I may get a little thirsty. I may take a sip of water. I may continue to speak again. So in other words, we are very concurrent in certain things we do. And given a timeline, we are progressing both on the talking and drinking water at the same time. So for example, if you put the pointer here on the timeline right there, you can say at this particular point in time, I have actually spoken a certain number of words and maybe taken a few ounces of water as well. So I made progress on both of those. And I can also check how many steps I took on my watch. And so I progressed on 3 different tasks. But I did progress on walking and the above task in parallel, but within them in concurrency. So we generally are fairly good at concurrent and parallel programming. We've done that for ages now. But as it turns out, we need to really think about something else as well, which really brings us to asynchronous programming. I know maybe nobody in this room likes to hear, but I'll say it only once because it's not something I want to repeat in public. So I'll just say it once. JavaScript got it right. That's it. I'm not going to say it again. Well, as it turns out, that this is actually a remarkable endeavor if you think about it. While most languages that we know of, name it, C++, Java, C#, and so many other languages, while they focused on parallel versus concurrent programming, JavaScript took a very bold step and said, nope, we're not going to give you parallel or concurrent programming. We're going to only give you asynchronous programming. So that was really remarkable for a language to take such a bold step in the past. And as it turns out, decades later, we are beginning to realize why this is extremely important. And the reason for that is we now live in a world of distributed computing, in the world of microservices and such. And as a result, it becomes really important for us to be able to do asynchronous programming. But what is asynchronous programming? Let's talk about that for a few minutes. So when it comes to asynchronous programming, it is really about So what is really asynchronous? It's really about non-blocking. But what in the world does non-blocking really mean? Well, if I need to make a call to get a piece of data, then I absolutely have to block until I get the piece of data. It doesn't make sense to say you ask for the data and you keep going. That makes no sense. It's like I go to the coffee shop and say, I'd like to have a latte, please. And then I walk away. And they're like, where's the person who ordered latte? Where did he go? Well, that wouldn't make any sense. If I want to have latte, I've got to wait on it. So in other words, what you can keep in mind is every task that needs a response, if you will have to block and wait for the response. So it doesn't really make sense to say it is non-blocking. So then what in the world does non-blocking mean? So it really it's really about non-blocking thread of execution. So that is really what we are focused on. So non-blocking is always about thread of execution. Your tasks have to block, because if your task doesn't block, it's not going to be able to make use of the data it requested for. So tasks are always blocking. And it's like, if I ask for a cup of coffee, I better wait for a coffee to arrive for me to be able to be drink. However, I hope you don't do the following. I think we can all agree. The very first thing you do when you get to work after waiting through all the traffic is drop your stuff on your desk and you go to get a cup of coffee, right? So when you go to get a cup of coffee, you realize that the coffee pot is empty. How dare somebody decided to empty the coffee pot and walk away? So you put the coffee in the machine, you turn on the machine, it starts brewing, and I hope you don't do the following. You don't stand there staring at the coffee machine brewing, and you're still like that people on the outside of the Buckingham Palace, and your colleague comes to you and says, hey, how's it going? And you don't respond, you don't move, because your eyes are focused on the coffee machine. You're so angry looking at the coffee machine for it to brew coffee. And they're like, should we call security? What happened to this dude not moving? I hope we don't do that, right? So what do? You turn on the coffee machine, it's brewing coffee, and you go to your colleague and say, hey, are you ready for the design meeting? And your colleague says, not yet, I need a few minutes to get ready. You say, fine. And you go on and turn on the email, and the email server is a little slow. It's downloading that email. In the meantime, you're browsing through a diagram that's part of your design. And somebody is asking you, what are you doing? And you say, I'm waiting for the stupid coffee machine to get me coffee. I'm waiting for my esteemed colleague to be ready for a meeting. I'm waiting for this email to be downloaded. And in the meantime, reviewing this document, what do you want? So the point really is, that's the non-blocking you. So there are 4 tasks that are running. You're waiting on all the 4 tasks to have completed so you can have a sip of coffee while you talk to your colleague, while you have the email ready for you to take a look at, but you're not blocking and waiting on those, the non-blocking, like a thread. So essentially, asynchronous programming is all about non-blocking thread of execution. We'll come back and talk a little bit more about this, but that really is the essence, is that when it comes to asynchronous programming, we are talking about non-blocking thread of execution, but tasks will have to block and wait. So then the question is, how do we program asynchronously? Well, I'm going to talk a little bit more about this towards the end to compare and contrast. We'll come back to that. But let's talk about how threads actually work so we can get a feel for how the threads are implemented, unfortunately, in the case of Java. So let's go back to Java for a minute. So I'm going to say in here, we want to create, let's say, a public, let's say static. We'll call it as a do work. And this function, I'm going to say, is simply doing the following. It is going to say, let's say, a thread dot, let's say, sleep. And I'm going to say sleep for about 5 seconds, let's say. And this is all this code is doing. it's going to sleep for about 5 seconds when you invoke it. So now I'm going to say int max is equal to 10, and I'm going to say I equal to 0. Let's say I less than max. Let's go ahead and say I plus plus. And I'm going to simply say here a thread, we'll call it as equal to new thread. And I'm going to say thread dot start. And actually, I'm going to start a thread of execution like so. I'm going to simply say over here dot start. So once we start the thread, I'm going to within this basically say, I'm going to call the do work method, as you can see right there. So once we call the do work, and outside of this, I'm going to simply ask it to, oh, let's say, wait for about 7 seconds right there. And I'm going to say, in this particular case, after the 7 seconds of delay, I'm going to simply say output, let's say, done. So we can see that it's going to say done when it finishes. So not a really exciting code, but nevertheless illustrates the idea we want to explore. So I'm going to fire up 10 different threads and wait for 7 seconds and say done. And you can see that it said done, not a problem, after the 7-second delay. So no big deal. It worked exactly as it's supposed to. So far, so good. However, notice that this particular code is starting 10 different threads and calling the methods on the thread. And what does the thread actually do? It calls a sleep method. Now let's think about the sleep method. What does the sleep method actually do? Well, the sleep method is going to pause the execution of the code for the duration of time. The problem really is, sadly, when a task blocks the thread that is, well, unfortunately, running the task also blocks. Now, let's entertain this thought just for a minute. Anyone in this room who has ever had to deal with a toddler in their life, what is the first lesson you learn as a caretaker of a toddler? When the toddler says, I want to sleep, the bad thing to say is, what a great idea, let me sleep alongside. If you sleep when the toddler sleeps, no work ever gets done. So as a smart adult, okay, as a responsible adult, when the toddler sleeps is when you do the dishes or other chores you have to take care of. Because sleeping when the toddler sleeps is the best way to get everything piled up and becomes very frustrating. But this thread is extremely misguided. The thread says, hey, what do you want to do? And the task says, I'd like to sleep. And the thread says, great idea, let's sleep. And so when the task is sleeping, the thread is sleeping. Now let's think about this for a minute. If your thread is blocked, when a task is blocked, what happens? It turns out, if this is an I/O operation, and if the I/O is making, if it's a user interface operation, like you clicked on a button, and when you're executing the action, if you were to perform an I/O operation where you're making a call to a remote service, and maybe that request is going to take a few fractions of seconds to respond. When your thread is blocked, your I/O becomes non-responsive. Not only that, if you have a request coming into your server, if the request processing thread is performing an I/O, the thread is busy processing the request, so it cannot handle new requests that come in. A case in point, I travel constantly, and this was a few months ago. It was 2 a.m. I had been on the flight for a good 36 hours. So at 2 a.m., I walk into the hotel. I'm quite wobbly. I would really like to go sleep right now. So as I walk into the hotel at 2 a.m., there is a clerk and there is a customer, and those are the only two people in front of me. And the clerk says, I would like to have an ID from you, please. And the person is like, oh, you want an ID? And I'm standing behind. It's like, please kill me right now. I want to go to my room. And as I travel, I'm the guy who travels with the passport in my pocket. So I have my passport right in my hand. Here I have it. check me in so I can go sleep right now. It's past 2 o'clock. And the person is like, oh, so you need an ID. Yeah, I would like to see maybe a passport. Oh, you want a passport. And the person goes through a binary search of where a passport is. And it's like, oh, you want a passport. Let me check where I have. And is going through the search of different parts of the body. And the clerk is watching patiently and having a humor at this person searching. And I'm like, excuse me, this is horrible. Because you are waiting for this person to finish the binary search of the passport when I have the passport ready here to get checked in. So what could this person have done? The person could have said, hey, why don't you continue your search? And once you find your passport, I will help you. And could have just taken a few steps to the next counter and said, may I help you get checked in? And that would have been fabulous, isn't it? But no, that person at the hotel desk was like the Java thread, getting stuck on the customer and not caring about any person waiting in the line. But that was fine for that hotel because I promise I will never go there. But if this was your Spring application or Quarkus or Micronaut, if your requests come in and you start processing requests on your request thread, your requests coming in are going to start piling up. And at some point, when your requests start piling up, there's only so many requests you can handle. So as a result, such mechanism has a direct impact on two things architecturally. It affects your system's scalability because there is only so many requests you can handle at the same time. So your scalability goes down the drain. But more important, your system has issues with availability because when the requests start piling up, when more requests come in, those requests get rejected because your queue has filled up. So you have both availability problem and the scalability problem. Oh my goodness, what do we do about it? Well, here's a way to fix it. Because you want better scalability and availability, let's put this application on the cloud so we can have a cluster of machines. And how do you tell your boss we need a cluster of machines? The honest response is going to be, we want cluster of machines because threads suck. That would be the honest response, isn't it? But they love this response because those people who are playing golf with each other are signing contract. But in the meantime, your company has to spend more money on cloud services. And also we are messing with the environment because we need a cluster of machines when we could have just done this problem with a single machine, but we couldn't do so. Why? Because our threads are really very poorly implemented. A case in point. When I go to this particular example here, let's go ahead and run this code just for the fun of it. And I'm going to say, this is going to be the code that we are interested in running. 7 seconds later, you can see that it tells us that it is done, so not a problem in terms of executing that code. But I go back to this code and say, hey, why don't you run 1,000 of those requests? Well, we are starting 1,000 requests at this point, and I should be able to handle 1,000 threads after all, isn't it? So about 7 seconds later, it's done, not a problem. But what if I ask it to execute 10,000 threads rather than 1,000 threads? If I go back and run the code now, as you can see in this particular case, that really failed. Hey, what's the problem? If you look at it, it says exception in thread main, out of memory error, unable to create native threads, possibly out of, it's not even sure. And it's basically saying, gosh, I cannot handle this load. And if you really think about it, somewhere between 1,000 and 10,000, it broke. Now think about scalability. If I cannot handle 10,000 requests for a code that actually does nothing but sleep, that's pretty sad, isn't it? And that is the state of threads that we have been having in Java all these years. Let's bring an analogy here just to understand it. Let's say you go to a really good restaurant. And what does a really good waiter in a restaurant do? The waiter comes to you and says, what would you like to drink? And you say, I'm not sure. What do you have? And the waiter gives you a list of things that are available. And then you say, I'm really not sure what I want to really drink. What would you recommend of the things you mentioned? If this is a terrible restaurant, what would the waiter do? The waiter will grab a chair, sit next to you and say, let's talk about your thoughts on drinking today. How's your day going, by the way? And 20 minutes later, the waiter is still trying to figure out what you want to drink. In the meantime, everyone else in the restaurant is completely angry because they've been sitting at their table with no food being served, and they get angry and they start leaving. That's not the way a restaurant would stay in business. And here's the irony. A good waiter actually doesn't wait. A good waiter makes you wait rather than them waiting. So the waiter says, why don't you think about it? I'll be right back, and buses around to other tables. And while you're having your meal, some waiter who is walking by may notice that you are low on water and may come and pour water as they are bussing around. I hope you dare not to say, stop it. You're not my waiter. How dare you pour water in my cup? That's the best way to get kicked out of the restaurant, because you don't care who is going to pour water as long as somebody is taking care of your thirst. So in other words, what if threads in Java can be like waiters in a good restaurant, where they don't block and wait, but they are focused on just keep moving and serving and doing work. And that's exactly what we want to do, is a non-blocking thread of execution. But we'll come back to that and take a look at it again, and I'll give you another example to look at it as well. So we talked about the impact on scalability and the consequences as well. But I want to really dive in and think a little bit more about this non-blocking nature so we can appreciate that a little bit more. So to do so, if you will allow me, I want to take a look at an example here in Kotlin and take a look at how this non-blocking nature can be really exciting. So I'm going to say import right there. Let's do a Kotlin x.coroutines, let's say .star. And I want to start with a little run. And I'm going to simply say over here, let's say calling 2 tasks. That's all I want to do for now. I'm going to say calling 2 tasks, and I want to display it. But of course, I want to display where I am calling this as well. So we'll say from, and we will say a thread dot current thread, and we'll display it. And as you can see in here, this is simply from the main thread. That's what's executing. And I want to emphasize this. In this example, I'm going to using only one thread, which is the main thread. So then I'm going to simply print out, we'll say called 2 tasks from the main thread as well. But of course, I want to make calls to 2 different tasks. So I'm going to say task 1, and I'm going to also call task 2 as well. Oh, by the way, Kotlin is a beautiful language. I truly like this language. Not only do I like Kotlin as a language, I personally think that the people who wrote Kotlin also are amazing human beings. I've had a chance to interact with them. I found them to be extremely intelligent, but also very passionate people. I just absolutely love the team. They are very great people. In fact, they're so good. They just don't want you to write code and go home. They care about not you writing code, but they care about how do you feel writing code as well. And to that end, beautifully, they decided to make sure you enjoy writing code, to make sure you're having fun when you write code. And just to remind that, they decided to call it as a fun task 1. So every time you write a function, you remember to have some fun and you are feeling good about it. So that's how you write a function in Kotlin, is by reminding yourselves to have fun. So fun task 1, and I'm going to go ahead and say entering task 1 here, and I'm going to say from, and we will simply output thread.current thread, and we will display the thread of execution right there as well. And I'm going to say exiting task 1 as well. Likewise, I want to go ahead and output a task 2, if you will, and it's entering task 2 and exiting task 2 as well. I know that's a bit of a boring example right now, but you can see we are calling 2 tasks, entering 1, exiting 1, entering 2, exiting 2, and call the 2 tasks, all of that in the main thread. And we know that's a pretty darn sequential execution. That's what you are looking at. However, I do want to make a change here, and I'm going to say run blocking. So what does run blocking really mean here? Well, run blocking actually starts what's called a coroutine. So as the name alludes to, a coroutine stands for cooperating routine. So you have 2 routines running at the same time, and you have a routine that can communicate with another routine. But in this case, it's starting what's called a parent coroutine. So the run blocking starts a parent coroutine, and the parent coroutine says, I will not go home until all the children coroutines complete as well. So the run blocking is for the parent not to finish until the children have finished. That's what run blocking means in this case. So in other words, Kotlin not only gives you the ability to do asynchronous programming, Kotlin also gives you this idea called structured concurrency. Now, a structured concurrency simply means there is a structure, in this case, a parent-child relationship, and the parent will stay around until the children are completed. If the child were to fail, the parent will automatically hear about the failure. The parent will abort execution upon the failure of a child, if you so configure that. And as a result, the parent will then terminate the other children because one of the child has failed. All that mechanism is baked into Kotlin's structured concurrency already. So given this, in this case, the output is not going to be any different in this particular case. As you can see, calling the 2 tasks, entering 1, exiting 1, entering 2, exiting 2, call the 2 tasks. However, I'm going to come down here and say launch task 1, and I'm going to say launch task 2 as well. So what does launch really do? A launch is a way for you to start a child coroutine. I want you to step back for a minute and think about the old times when you used to develop a Swing application or develop a desktop application like a Windows program. Remember what you did in those applications. When a button is clicked, you didn't run code right away. When a button was clicked, you put a message in the message queue that said, here is a handle event that you need to handle once you have completed your current task. When your Windows thread finishes its execution, it's an idle. It goes to the queue and picks up one of the event handlers, executes it, and goes and picks the next event from the queue. If you remember that mechanism of how events are handled, that's very similar to this one. Because when you come into the code, the minute you hit the launch, you're not launching anything. You just put an entry in the queue and you moved on to the next function. The next was a launch as well. You put 2 entries in the queue. And then you execute the rest of the code. You hit the end of it. Am I done yet? No. Your queue has messages to run. So go run task 1. Am I done yet? No, you have one more message in the queue. Run task 2. So as a result, when you see the output this time, it is different. You said calling 2 tasks, but it says called 2 tasks as well. That shows that that is non-blocking. But notice it went to task 1, finished task 1, went to task 2, finished task 2 as well. So the non-blocking nature of the main thread becomes a bit more clearer here. So the thread comes in, calls the calling function, puts an entry for task 1, puts an entry for task 2, did not block to execute any one of them, ran the last function, the print line, called the 2 tasks, then goes and picks up task 1 and executes it, and picks up task 2 and executes it. But as it turns out, we can do a little bit more than this as well. We can say delay 100, and I can say delay 100 here as well. So you're telling the task 1, execute this, but hit a point where I want you to delay the execution like you are doing an I/O. But remember, when you delay, what you don't want to do is to tell the thread, come sit next to me here. While I watch time go by, you can watch me watch time go by, because that would not be a good use of the thread. But until this point, everything is good. And I did mention to you that I really like Kotlin. I mentioned to you that the people who wrote Kotlin are some of the best people in the world. None of that changes from what I'm going to say you now. But I do have one complaint to make, however. I really wish that the Kotlin team had paused to think a little bit. Maybe they could have called me and they could have said, Venkat, what do you think? I would have given them my advice. I would have given them my advice to say, this is non-blocking fun. How does that sound to you? Non-blocking fun. Okay, maybe that's not impressive. How about never-ending fun? That would be really cool, isn't it? But they did not think through this, honestly. It breaks my heart. It truly breaks my heart. They instead decided to call it as suspend fun. How terrible that really is. How do I tell people? What, didn't you say it was fun? Now you're suspending fun. I'm telling you, this is one petition I have with them to rename this as never-ending fun, right? Or non-blocking fun would be really nice too. But for now, it's called suspend fun. So, but what does suspend mean? A suspend is an annotation that really gives a clue to the compiler that this function may not run to completion, that while it's executing, you might suspend the thread of execution so the thread can go do something else. So as a result, when you execute this code, notice the difference. First, everything here is in the main thread. This is not multi-threaded. It is asynchronous. Everything here is in the main thread. What did the main thread do? It says calling the two tasks. It then said called the two tasks. Then it says entering task 1. But notice it says entering task 2. And then it's exiting from task 1 and then exiting from task 2. So if you catch this particular thread right in the middle here, you ask the thread, where are you? And the thread says, I'm in 3 places all at the same time. I left some work undone in task 1 because it's waiting. I left some task in task 2 because it's waiting. And I'm at the bottom of the parent coroutine because it's waiting for the children. I am in 3 different places. Just like you waiting for coffee to fill up, for your colleague to be ready for the meeting, for the email to download, and you're in the middle of 3 things. That's the non-blocking thread that I talked about earlier. So while the tasks are blocking, your thread is non-blocking. And when a thread is non-blocking, that allows you to reuse the thread for more things it can do. And as a result, you will need fewer threads to be available in your system. And the result of that is more scalability, more availability, fewer resources you need to use, better savings on your money, and better for the environment as well. So we are able to see how the non-blocking nature of this works is the same thread is multitasking between multiple things and not just sitting there and twiddling away, waiting for the task to complete. So that's basically what we saw with this particular example in Kotlin. But before we leave Kotlin, let's do a quick comparison of this to what Java is doing. Well, first of all, Kotlin coroutines is bundled with the idea of structured concurrency. In Kotlin, you don't do asynchronous versus structured concurrency. It's part and parcel of one. You do one, you do the other. So it manages this hierarchy of concurrency. It gives you finer grained control. You can send a dispatcher to the coroutine, and the dispatcher can be configured to say how it should behave in terms of threading, in terms of where the task is executing, how exceptions are handled, how the parents behave when a child were to fail. All of that can be configured using structured concurrency. So in Kotlin, your concurrency, your coroutines and the structured coroutines are part and parcel of one thing. That is the first plus point. The second plus point is you don't need anything from Java for you to benefit from structured concurrency in Kotlin. You say, I've got a Java 8 application. I don't want anyone to know about it, that I'm still using Java 8. But I want to do concurrency in it, can I? And Kotlin says, we are still friends. I will never tell anyone you're running this on Java 8, but you can benefit from all the concurrency. You don't have to go all the way to Java 21 in order to benefit from asynchronous programming. Just don't tell this to the bosses. Then they say, gosh, that means we can be on Java 8 forever, right? No, don't give that idea to them. But the point is, you can be using reasonably almost any version of Java, and you can benefit from structured concurrency using Kotlin as well. Now, as time moves on, there is a good high possibility that Kotlin will move forward and re-implement their concurrency, their coroutine, to make use of virtual threads. And if they do, that's going to be an implementation detail, and you shouldn't care about it, except knowing that is using much better facilities under the hood than it would otherwise be. Not only that, not only do you get coroutines on the JVM, because Kotlin is a multi-platform language, you get to enjoy coroutine on the JVM, but also on WebAssembly or a native deployment or Android or other environments where you may deploy your Kotlin application. Because the Kotlin coroutines are an abstraction at the language level and library level that gets mapped into the underlying system. So if you're doing multi-platform programming and you want asynchronous programming consistently, you get that through Kotlin. That's a benefit as well. But of course, to be objective, I gave you the praises for why Kotlin coroutine is great, but there is one disadvantage though, and that is if you want to really make use of a suspendable function, you got to mark your function as suspend. And then the function that calls it has to be a suspendable function too. And this spreads like a disease. And you keep propagating this suspend, and at some point you will use curse words because you're like, I want to call it from this function, but I cannot. Why? Oh, darn it, this function is not suspendable. Now I got to find a way to make it suspendable. It can get quite annoying if you did not design for this already. Retrofitting this into existing code can be a pain in the neck. So that's one disadvantage of this approach, is the fact that you have, which is something that folks behind Java took pains to make sure they don't and make it very seamless. And that's basically what we're going to see in a few minutes. So coming back to Java, what are virtual threads? The first thing I want to emphasize is Java completely separates asynchronous programming from the structured concurrency. You don't get them in one parcel in Java. In Java 21, you have virtual threads. In Java 23, actually 22 and onwards, in a pre-release, you have structured concurrency. And if you are using LTS version like Java 21, you have virtual threads, but you don't have structured concurrency. When structured concurrency becomes a part of the final release, I don't know. I'm suspecting maybe Java 25. We don't know. And when it happens, you can use either virtual threads or you can also use structured concurrency, but you got to opt in for them separately. They're not as mixed in together and integrated as in the case of Kotlin. But I'm going to focus on virtual threads. So what are virtual threads? Well, we saw the problem with threads in Java because when a task blocks, the thread blocks, and that's no good. So what do? Well, Java decided to go the route of what are called virtual threads. So what are virtual threads? Virtual threads are called super lightweight threads. You say, whoa, time out. Why the word super lightweight? As it turns out, the words lightweight was taken. So they had to come up with something better than lightweight, so they called it super lightweight. So a super lightweight because it's lightweight compared to threads which are lightweight. And so the word lightweight is pretty relative. And a super lightweight is lighter than lightweight. And while threads are lightweight, virtual threads are a lot more inexpensive to create. But how does this work? So essentially, it is really going back to an amazing idea in computer science. So let me take a tangent for a minute, if you would permit. If you ask me, who should be given an award in computer science? And I would say the award goes to only one person in my mind. Unfortunately, he passed away. But he was a British computer scientist, a gentleman named David Wheeler. Because David Wheeler said something so profound that every single day, any programmer on earth lives his words. We benefit from his work because this is the way we write programs. So what did David Wheeler say? He said, in computer science, in computer science, we can solve almost any problem. I think he was being modest. I would have said we can solve any problem, but he's better than me. He said we can solve almost any problem by introducing, he said, one more level of indirection. And to me, this is one of the most profound words ever, in my opinion, because if you think about this, it's a level of indirection that consistently has helped us to solve problems in our field. So what does level of indirection mean? As an example, when you think about procedural programming, like in C, what do? We use pointers, isn't it? So we use pointers, and by using pointers, pointers provide a level of indirection in the code. So rather than referring to a function, you are using a pointer that refers to a function. That's your indirection. You can change the pointer and execute a different function. And that gives you the power to be very flexible. So in procedural programming, we use pointers. Pointers provide the level of indirection. You say, okay, that's great. But what about object-oriented programming? In object-oriented programming, we use polymorphism. Polymorphism gives us a level of indirection. Because what does polymorphism mean? Go ahead and call a function. Go ahead, right ahead. But the function that gets called is not the one you think will get called at compile time. But the one that gets called is based on the runtime type of the reference not the compile time type you know of. That's what polymorphism says. That's a level of interaction. You are firing a method, but the one that gets called is resolved during runtime. We call it dynamic binding in object-oriented programming. That is a level of interaction. You say, all right, that's cool, but what about functional programming? Well, in functional programming, we pass around lambdas. And when you pass a lambda to a function, that function may call the lambda or bypass calling the lambda or pass the lambda to yet another function. And you can decide which lambda to call to which function. So it becomes a reference to a function, much like a pointer is. So functional programming gives you level of interaction as well. What JVM team did is took this idea of interaction from these programming models and took it all the way to concurrent programming as well. And so, as it turns out, virtual threads are a level of interaction. So essentially, there are two threads, virtual threads and career threads. So you have two different threads available for you. And in this case, when a task blocks a virtual thread, running it blocks as well. So that's no different from what we know today. When a task blocks, the thread blocks. But in this case, when a task blocks, the virtual thread actually blocks. But as it turns out, when a virtual thread blocks, what happens in this particular case? When a virtual thread blocks, it gets an unmounted from a career thread. So essentially, it gets unmounted from a career thread. When a task is ready to run, the virtual thread gets mounted on a career thread at this particular time and resumes execution. So think about it like a horse rider. A horse rider is riding on a horse. Well, they decide to take a break. The horse rider unmounts from a horse. And now the horse can graze around while the rider can walk around. But the rider decides to ride again, but potentially can grab one of the horses available, mount on the horse, and take the ride. So think of a virtual thread as a horse rider. Think of a career thread as the horse. So in other words, when a task needs to execute, the virtual thread mounts on a thread, executes. When the task passes, the virtual thread unmounts. The thread can be relieved to go do other things. When the task is ready to execute, the virtual thread gets remounted on a thread and executes it moving forward. So, of course, one small detail. The career threads are the threads from the operating system. The virtual threads are the threads created on the JVM. So they are not really threads under the hood. So let's entertain this thought just a little bit to understand what this means to us. So going back to this example, as you recollect, when we ran this code, it failed miserably at 10,000 threads, and that couldn't simply take it at all. But let's go back to the modest value of 10 for a minute, and I'm going to go back here and say, not a new thread, but say thread dot, let's say start virtual thread. And I'm going to start a virtual thread right there in the execution. So rather than creating a thread, I decided to create a virtual thread at this time. So what's going to happen by creating a virtual thread? So I go run this code right now, and you can see 7 seconds later, it says done, so not a big deal. However, I'm going to bump it up to 1,000, and as we know, 1,000 was not a problem for a thread, it shouldn't be a problem for a virtual thread either. And you can see in this case, that was not a problem. But I'm going to make it a 10,000. If you remember, we couldn't handle 10,000 threads. Why is this very different? The reason is you're running this in a virtual thread. So when a virtual thread executes your do work, the sleep method that you called executes now in a virtual thread rather than a real thread. And when your task says, oh, I need a break, I want to sleep for 5 seconds, the virtual thread says, that's a great idea. Let's sleep. But before I do, honey, just give me a second. Let me unmount from my thread that's running me so we can peacefully get some sleep. So this is an adult who can actually sleep when the toddler is sleeping, but the adult delegates the job to somebody else very smartly. So the virtual thread unmounts from the career thread when it hits the sleep. So while it's sleeping for the task to complete, the thread goes away and can do other things rather than having to wait. So as a result, when I execute this code with a virtual thread as opposed to using a real thread, that was not a problem. It did not fail. Now, of course, you say, really? Can I now go back to this and say 50,000 threads? So I'm going to ask you to run 50,000 threads, in this case, virtual threads, isn't it? And the virtual threads, did you hear that? It just said, why don't you give me something more challenging? And so you say, really, how about 100,000 threads? Do you feel the pressure in your blood? Do you feel like a little tension? It's like, oh my gosh, are you kidding me? 100,000 threads. And you throw 100,000 threads on it, and what does it do? It doesn't even break a sweat. And it's like, I told you to give me something more challenging. Didn't you hear me? And you're like, really? How about 1,000,000 threads? Seriously, right? 1,000,000 threads. And you say, go, start 1,000,000 threads for me. And the virtual threads is saying, you quite didn't get me when I said, give me something more challenging, did you? So the question is, how many threads can you create? And the answer is, how many ever you need. And it doesn't really matter. And somebody said, oh my gosh, but there is an upper limit, isn't it? And the answer is, if you're worried about that limit, you got to have a talk with your architect, because you need to really ask the question, what are you building? But within reason, this is not a problem at all. And so you say, oh my goodness, what's going on in this particular case? Well, as we talked about, there's a mounting and unmounting that's happening behind the scenes. And because we are mounting and unmounting, it doesn't have to hold your resources. And what's the benefit? The benefit is when you have a system where you're performing I/O operations, you don't have to block and wait for the I/O to complete. And in the time, deprive other requests that come in. Like the clerk in the hotel who was completely insensitive to me waiting there at 2 a.m. And instead of that clerk was running on a virtual thread, the person doing binary search for their passport would have seen an illusion of the clerk, but the underlying clerk would have moved away and started helping me on the other side. And I could have been in my room sleeping while this person is completing their binary search of where their passport is. So the point really is we want to think about throughput. We want to think about scalability. We want to think about availability. But let's get a little deeper into this so we can actually see this in action, so we can appreciate this a little bit more. So I'm going to go back here and say max is equal to, let's bring in 1,000. After all, I didn't have a problem creating 1,000 threads, isn't it? So I'm going to say 1,000. But then what do I want to do within here? Well, I'm going to say, in this case, let's go ahead and say I want to run all these 1,000 tasks at the same time. You probably are thinking, wait a second, I went with your example so far, but you did something that's absolutely stupid. You did new thread. The last time I saw anyone do new thread was 1997. Why in the world would you create a new thread? That makes no sense. Oh, completely agree with you. Because you wouldn't let anybody just do a new thread in your application. That's kind of silly, isn't it? So what would you do? Oh my gosh, you got to use executor services, right? Absolutely. So I'm going to say java.util.concurrent.star. Let's go ahead and say var executive, let's say service is equal to executors dot new fixed, let's say, thread pool of max. So I created a pool of 1,000 threads because I really want to do an operation of 1,000 executions. Now, typically what you may do is create 500 threads and schedule job on the thread, which means if you are exhausted all these 500 threads, you keep waiting for something to be ready, isn't it? So which means you are lowering concurrency and you're waiting for things to finish. Well, that's fine. So executor service, right? So executor service. So executor service dot, let's say, shut down. And then I can say executor service dot, let's say, await termination. And let's say time unit dot seconds. And I'm giving a generous amount of time for it to finish. Now, this is obviously going to tell me I need to handle an exception on that particular call. But as experienced Java programmers, we know exactly how to handle exceptions. So let's take care of that right here, right? So in this case, we got a little code that's starting an executor service and shutting it down when it's done. Great. Now I'm going to say a public static, let's say a void do, I will call it fetch. But I'm going to say index right there. But within this, I'm going to output. Let's go ahead and say a enter plus, let's go ahead and say in this case, I would say index plus, would say a enter. And this is going to be a thread dot current thread, so we can display the thread of execution. I will also say an exit as well. And I just want to display when it's entering, when it's exiting. But within this, I'm going to say try and catch. I'm not interested in the exception as much at the moment, so I'm going to leave it blank intentionally. But within this, I'm going to say Java, well, let's go ahead and say Java dot, let's say nio dot file dot star, and we will say over here a file of let's say files dot, let's say lines paths dot get, and I'll say sample dot java, the file in which I am, dot count, and I'm asking it to read the number of lines in the file. Once it reads the number of lines in the file, I will say in a after, and in the a after, well, this is going to print out after this. So we will simply say this is going to be the enter. This is going to be the after the execution. So I will say this is going to be after, right? So E F. Okay, maybe it's going to sort it. We'll see. So there's an after. Then I'm going to print after the call the details of the thread as well. This is going to be really easy to see in here. So I'm going to say executor service dot submit, and what am I submitting right here? So for let's say I equal to 0, I less than max, I plus plus, and within this, I'm going to simply say int index is equal to I, and submit will simply say fetch and pass the index to it. So we are calling the method right there when we are executing it, right? I'm going to take a very simple scenario for now. I'll come to a higher number a little later on so we can appreciate that a lot better. So I want to run the code and see what it wants to tell me. So right there is the output. I'm going to take that and I'm going to sort it, and then I'm going to display that right there. So let's take a look at what we see in here. Notice what it produces in this particular case. You have a thread 1, just to take a random one, that is thread 4. Take another random one, that is thread 8. So you can see that the entire task from the start to finish is carried out by one single thread. So what do we know about it? When you're performing I/O, the thread says, you go ahead, make an I/O call, I'll be waiting here for you. And when you're back, I'm ready to run. What are you going to do when I'm waiting for the I/O? Oh, I'm just going to sit here and think about meaning of life, right? So it's not doing anything, blocking and wasting its resource. That's the way it's working, isn't it? Now, let's switch a little bit to this. And I want to convert this to using not the executor service with a new fixed thread pool, but I want to use virtual threads. But before we use a virtual thread, what is this line of code going to change is the question. Before we make the change to that line of code, let's talk a little bit about virtual threads. Now, it makes sense to create a pool of threads and be able to reuse them. But it doesn't make any sense to create a pool of virtual threads, because virtual threads are cheap. When virtual threads are cheap, you put more effort to reuse them than to simply discard and create a new one. When something is cheap, it takes more effort to reuse it than to simply get a new one. So as a result, when you look at the executor service, if you will, notice executors dot, and there is the new virtual thread per task executor. So this executor service says, I will give you the executor services interface, but every time you schedule a task, I am not going to pull a thread from a pool, but instead, I'm going to spin up a new virtual thread and give it to you. And that's exactly what this is telling us, right? So it's a new virtual thread per task executor. So now that we saw that method, let's just call it right there. So I go back here, and I'm going to run this code one more time. Let's take a look at the output it produces this time and see what we learned from this. Let's take a random one. Look at this one. What do you notice? The entire task from start to finish was executed by virtual thread number 32. The virtual thread 32 said, I am in charge of you running. I'm going to stay with you from start to finish. That's why it's virtual thread 32. But guess what happened? When you entered, it got mounted on worker 4. When you made the I/O call, it got unmounted. And after, it is on worker 2. And when you finished that and came out of that, it mounted on worker 9. So the same virtual thread 32 got mounted and unmounted 3 times over in this particular case. So there's a constant mounting and unmounting happening. Likewise, let's take another random one. Here is the ID 7. The virtual thread is 36 entirely, but it got mounted on worker 8, got mounted on worker 1, got mounted on worker 2. And you can see how it again mounted and unmounted 3 times. What is the consequence of this code is the question. Let's get a little deeper into this. Let's go back to this code, if you will. And I'm going to remove this print from here, and this print here, and this print here as well. So we don't have the noisy output anymore, right? So we got rid of those. I'm going to go back here to the main. And in the main, I'm going to say try thread.sleep. This is in the main thread, right? And I'm going to say 20,000 because I'm extremely slow. So I'm going to give myself a 20-second delay. And I say exception EX. Let's do that. And I'm going to say running right after that. And when I'm done with it, when I'm finished with it, and I'm also going to sleep for another 20 seconds for things to calm down. So I gave myself a buffer of 20 seconds and a 20-second before I came in and executed this code. So I'm going to go ahead and run this code right here. And as you would expect, a 20-second later, it's going to say running. And a 20-second later, it's going to finish the job. And it's going to say, finish up and exit right after that. So that's a nice buffer I created for myself in that code right there, as you can see. So we'll come back and take a look at what that's going to do in a minute. So there you go. It says running. Maybe the 20 seconds is a little too much, but that's OK. And I'm going to go back to this code and say, this is 1,000 requests coming in. So let's go back to this code and provide this right here with the regular threads, as you can see. So I'm going to go back and run this code. That started. I say JPS, right there is the process, JConsole, and I'm pulling up JConsole on it. I say go run the code, show me the threads, and I'm going to read this for you because the font size is small. It is telling me there are 15 threads that are running. Sure enough, because I just started the program, right? But now it says running. Did you notice the number? 1,015 is the count. So my program is using 1,015 threads at the peak of it. Now that means to do 1,000 operations, I'm using 1,000 threads. You can see the curve right there. It went up, stayed there, and came down. What that means is I'm using 1,000 threads to run this code, right? Great. Let's kill that now. Let's go back to this code and comment this up and go ahead and uncomment the next line. We are using virtual threads now. That's all we are doing. Let's go back and run the code again. Let's run JPS. Here comes the code. Let's run JConsole on that. Let's connect to it. Let's ask it to show the threads. That's exactly 15 threads, as we saw, no different. We're waiting for the 20 seconds to clear. It's going to say running. And when it starts running, notice how many threads we ended up using. 40 threads in this code. 40 threads, not 1,000 threads. Why? Because when our threads hit the I/O, the virtual threads got unmounted. So as a result, they said, damn, I don't really need that many threads. So rather than using 1,000 threads, you ended up using 40 threads. Just to enter in this thought one more time as a final example here. If I go back to this and say, give me the regular threads again, but bump this to 2,000 threads. I think you know what the answer is going to be for that, right? So when you run the code, here is the process. I'm going to say JConsole and fire it up with that and take a look at, so that was wrong. So JPS, oops, wrong one. Let me try this. So JConsole and fire it up. And here is the number of threads I want to see. So how many threads are we noticing? You can see 2,016 threads. So the number of threads is equal to the number of tasks that you're running in the code. That's what you're seeing. As you would see, it's going to come down crashing from those 2,000 threads when the execution is completed, as you would imagine. Well, on the other hand, if I were to go back and use virtual threads rather than using regular threads with 2,000 threads, what's going to happen? 2,000 tasks, what's going to happen is the question, right? So here comes the task, and I say JConsole again. Let's go ahead and fire it up. Take a look at the number of threads it's going to use. We're waiting for it to start at the time. So when it hits the running, for the 2,000 tasks, rather than creating 2,000 threads, how many does it end up doing? 40 threads still, because it says, I started those tasks and I can release you and you can go do more work. So you went to 2,000 tasks, but you did not make a dent on the number of threads you are using in your system. Imagine what kind of impact you're going to have on scalability. Now imagine you turn on the flag in Spring and tell Spring, don't do the work in real threads. Do the work in virtual threads. Your requests keep coming in, and your request fire up IO and unmount. So the request thread can go back to the front and pull more requests, throw them on IO, and go back for more requests. Your system suddenly becomes much better in terms of scale without having to go through multiple machines. And your single box now can scale a lot better because you're not holding threads hostage. And instead, you are releasing the thread saying, you go do other work while I'm waiting on this IO. When it's done, I will request for a thread, you can provide it, and I will mount on it and execute it. So threads mount and unmount constantly in what they do. So we saw the behavior of IO. We saw the usage of the threads and usage of virtual threads. So that brings us to the question, why do we want to program this? There are a couple of reasons why we want to program this. The first is scalability, as you saw. But scalability is not the only reason to do this. If you wanted scalability, you already have it because you can program asynchronously. But ignore virtual threads for just a minute. How do you program asynchronous in Java? Well, you can use the functions of the NIO, and you can use a file async. And then you can start using callback functions. When you use callback function, your code structure is very different from a sequential code you would have written. And with callbacks, your code is horrible to understand, horrible to maintain, horrible to handle exception, and it sucks the life out of you when you start writing it. In fact, in a friendly way, you call it the callback hell. And that's no fun to write such code. So the code is extremely hard to maintain. You go to your architect and say, I want to write asynchronous code. And what does your architect say? Hold on, don't venture into it because that's expensive. If we don't need it, we don't want to waste our time doing it. And then 7 months from now, you realize we have to make it asynchronous. And the architect said, I turned in my resignation last week already because this is going to take us 3 more months to implement. I don't want them to know and fire me, so I quit already because the cost of change is horrible. So what does the architect do the next time? Says, let's think much more about this. Do we really want asynchronous? Then let's start programming it sooner because it's expensive to do it later. It has an impact on your architecture. You say, well, I got an idea. Let's not do that. Let's use completable future. Raise your hand if you're used completable future in a happy way. That's the, yeah, and there's no hand that stays up. Why? Because completable future is great as long as you don't use it. Because the minute you start writing code with completable future, what do you realize? Exception handling is a complete mess because your code structure is like this. And you're like, how's the sequence now? It's a functional pipeline, but this set of function is called on a happy path. That set of function is called on an unhappy path, and you're trying to really understand which path is which, and everything is in one line, but it's all kind of braided together, and you cannot keep yourself sane understanding this code. And you say, my gosh, I don't want to maintain this code. So complete the future is something that's completely horrible. Now, take a look at the code we just wrote. The structure of this code is exactly the same, whether you ran it synchronous or you ran it asynchronous. I did not touch the highlighted code at all. What change did I make to that code to run it synchronous? And what change did I make to that code to run it asynchronous? The short answer, nothing. I did not touch the highlighted code at all. So the structure of synchronous versus asynchronous is exactly the same. And you can handle exceptions to your hard content because that's what we are good at when we write imperative style code. There is no callback hell. There is no braided calls to go through and understand. And then away from that, right here, you are switching this between synchronous versus asynchronous to say, I want this to run a regular thread. I want that to run a virtual thread. In a way, I would use the word, in this case, using virtual thread is simply an aspect, as in AOP. So in aspect-oriented programming, what do? You do a cross-cutting concern. Right at the top level, you're saying, everything over there, I'm going to control here with a switch. Flip to the left. It's running in a regular thread. Flip to the right. It's running in a virtual thread. Synchronous, asynchronous. That was your synchronous to asynchronous switch. So you flip that up, it's synchronous. You flip that down, that's asynchronous. So how cool that is. As an architect, you sit there and have a good time. You're telling your team, don't worry about asynchronous. If it's not important, we don't have to worry about it. Hey, what if it's important? Just let me know, and I'll flip the switch and it's asynchronous now. Because the cost of change is minimum. What happens when a cost of change is minimum? You eliminate the risk of that change. You get to enjoy the last responsible moment. You're not dreading over synchronous versus asynchronous because it resets your playing field. So one of the cool things that Java has done is it completely reset the playing field. Before the time of virtual threads, asynchronous is an architectural decision that is expensive to make. Virtual thread says, hold my drink, and I will make this trivial for you, so you don't have to worry about it at all, right? And that is the power. This is why this is not just a programming exercise. It has a huge impact on your architectural decisions. And I think that's why this particular idea is amazingly popular. If you ask me, for all the things we have seen in Java, what's the most powerful? And you would expect me to say Java 8 lambdas. Sure, that's great from the programming point of view. But from the scalability and architecture point of view, virtual threads is the one that makes the difference for me. And that's the cool thing about it. Hope that was useful. That's all I have. Thank you.
Thank you. Thank you, Venkat. Does anyone have a question? I think you have a couple minutes.
Well, I have a lot of time.
Okay. Awesome. Yeah.
Oh, I think that's active probably.
That one's, that's why I almost, okay. That one or which one should I be? This, okay. Anybody has a question for Venkat?
I just wanted to comment that, it's been, the shorter word as opposed to never ending.
Yeah.
But I.
Oh, come on. Awesome.
Thank you. Anyone has question? No? I think we have someone.
So we'll call it super fun. Yes, please.
realize, where have you seen the use of Java virtual threads?
Yes. So typically, your goal is to scale your services. So my argument is, if you are using Spring 3.0, you're going to reach for this flag very quickly. And in fact, Spring makes it insanely trivial. You just add one flag, virtual thread true, and you're done. And now you are spinning request on a virtual thread. So what does that mean? As an example, right? I've got a client who is in the financial world. They get a request on their Spring application. And when they receive the request, based on the customer, let's say Sam, hey, here's a Sam sending request, but Sam has 15 accounts. So they literally make 15 requests to backend services. They aggregate the 15 responses and then send a response to the user to say, here are all your accounts, here are all your balances, and various other details. You can imagine making 15 requests in the backend is enormously slow. Even if it was really fast, it's still slow because you're making network calls. And while that network call is being made, you are blocking and waiting for the request to finish. So now you're asking, how do I amortize that cost? Oh, we could use completable future, or we could use reactive programming. But all that extra complexity is just to make sure you're not holding your threads. So their coding was expensive to make this happen. With virtual threads, it becomes trivial. You just go through a loop and make the calls in a virtual thread, and boom, you're done. And your request is blocking and waiting, but your thread is not blocking and waiting. So you get the best of both worlds, because when your request is done, you're sending the response. But in the meantime, your thread is, hang on, while you are working on it, let me go serve other users, right? So you're able to process more requests. The throughput increases in your system. Why? Because when in a regular system, let's say I'm going to take 10 seconds to respond, hypothetically speaking, right? Exaggerated. So while I'm taking 10 seconds to respond, take a hypothetical example of only one request is handled, right? In this case. So I get two requests. One is working, the other is waiting. When the 10 seconds is over is when the next request can come in. So the time for the second request is 20 seconds, out of which 10 seconds is went on waiting. The third one is even more punished. Now, all the requests are going to take 10 seconds, because all the request is doing is taking a request, throwing it on the IO, and going and serving the next one. While this is waiting, the second one can end up waiting too. So your throughput increases in your system without increasing the demand on your system. So the answer to your question, are you building any application with Spring, Quarkus, Micronaut, name your web server container, you're going to benefit from this. So that is the beauty. Reactive programming can scale your services. Virtual thread scales your servers. So your server application scales immensely because of this particular scenario. The place where you want to use this is when you have I/O. It makes zero sense to do computations on a virtual thread, because your computations are going to hold on to your CPU running. Don't ever put computations on virtual threads, because you're wasting it. So this makes really good sense in any I/O bound. And most web servers are I/O bound because they make backend calls to remote web services, remote microservices. Absolutely.
Thank you.
Please.
Thank you. Someone, yeah,
Thank you, Mary.
yeah, no problem. Okay.
And you're doing the
First
right
and
thing
Dan.
to ask questions from the farthest end, so you can give more steps for Mary. So that's good, in all good intention.
No, don't worry.
Spendable. What's the cost of maintenance of spendable? Why just not make every function suspendable?
Ooh, that's a good question. Why not make every function suspendable? There's a reason why you don't want to do it. There is a cost associated with making functions suspendable. What I did not show you is something we need to be a little bit aware of. So let me, if you don't mind, let me show you real quick. So let's get rid of all of that for a second. And I'm going to just go back here, and I'm going to simply say, here is a fun task 1. That's all I have. And let's just simply say here's an n, which is an integer, and all it's going to do is simply return what's given to it. So it's a very trivial function, right? Nothing really exciting. So I'm going to go back here to this function now, and I'm going to say over here, let's say Kotlin C dash JVM, and I'm going to just compile this stuff and take a look at it. So when I compile this to a bytecode, you can see in this case, sample.class, let's take a look at the bytecode, if you will. What you notice here is nothing really exciting. All you do is look at the final int task1. It's a regular function, right? No big deal. However, if I go back to this code, and if I say suspend, that's all the change I made, nothing else. I just made it a suspend function. That's all I did. Now I go back and run Kotlin compiler, and I'm going to say Java P one more time, and take a look at the bytecode. And if you notice the bytecode, notice what you see in the bytecode. All of a sudden, in the bytecode, we called it task 1, right? Look at the task 1. It is actually passing a continuation behind the scenes. So a compiler is doing a lot of extra work when your function is suspendable. That's an overhead you don't want if you're just making regular calls, because the compiler is going to constantly be sifting data that it is to store before making the call, and then when the call completes, or expecting something to be intermediate to store it. That's a lot of overhead you don't want to incur when you don't have a need for it. A second problem, if you do have a suspend everywhere, and your colleague comes to you and says, I have nothing to do with asynchronous, I have a regular function, can I call your function? You say no. You got to make your function suspend, because you can only call suspendable functions from other suspendable functions. Your colleagues no longer want to be your friends. They suspend that. Yeah, it is exactly the same problem that gets propagated. Yep, that's right.
Thank you. And one question about structured concurrency with virtual thread. You mentioned it's going to ship in 23 or
But 25 most likely. Yep.
dependency on any other checks. What's the problem?
Yeah. So the structured concurrency is built entirely on virtual threads. So that's the dependency, really. So when you create a scoped task, your scoped task automatically runs in a virtual thread. So that's the dependency, really. And it also depends on a lot of things it does behind the scenes. Like, for example, preempting task. When a child fails, it can communicate with the parent, and the parent can decide what to do about it. So all that mechanism is built in. But as far as dependency is concerned, it's depending on virtual thread. Why didn't they release it together? It's a question of priority. There's only so much they're able to do at any given time. So they had to focus on virtual threads before focusing on structured concurrency.
What structured concurrency is going to be the API microservice? Not going to be they will expect you to use virtual thread with structured concurrency creation docs.
You can use virtual threads without using structured concurrency. Not a problem at all. If you're using structured concurrency without even you thinking about it, virtual threads play a role behind the scenes. Because the main reason to do structured concurrency is to manage the hierarchy of parent and child when you perform I/O. That's the real purpose of it. So the dependency on virtual threads is more implicit than being explicit. You're not going to do any configurations. In fact, in the beginning, unless you know already, you may not even realize you're using virtual threads when you do structured concurrency.
So they're not the expectation is
Not at all, not at all. You're not forced to use it at all. It's an opt-in. If you don't want to use structured concurrency, you don't have to. So let's step back and ask the question, why would I care to use it? The reason you would care to use it is, right now, when you're doing executor service, you don't have ability to preempt task unless you implement a poison pill approach in your code all by yourself. So you're saying, here's my parent task. I created these children. A child failed. I want to propagate to other children. How do I do it? Good luck. You got to write a lot of code for it. Well, that's the problem you're going to solve trivially by switching over to structured concurrency, because that's built in. You say, but my work use case doesn't have such a need. I've got all these tasks independent. I don't have a parent-child relationship. I would say you have no reason to use structured concurrency. So that's why it's an opt-in. It is for a very specific use case, and then it solves your problem really nicely.
Thank you.
Thank you.
Dan.
Okay, so I have this problem where I have master orchestrators. And I'm thinking you can't use two levels of virtual threads like that. Is that correct? Because the virtual threads inside the virtual threads are never blocked.
The virtual threads inside a virtual thread will never block.
Virtual threads. Those virtual threads are never blocked, so the original ones will never change to the next task.
Actually, they will block. So your tasks, if your task is blocking, your virtual threads will block, but they will get unmounted from the real threads. So in this scenario, let's take a little bit more detail here. Let's say I have an executor service, which is made up of virtual threads. And within that, one of the submit methods, I call a function foo. And now I am in the foo function. I am making a call to yet another function, which in itself starts another executor service. And within that executor service, I'm making a call to a function which performs an I/O. Well, now I have the parent virtual thread, which is blocked, and the child virtual thread, which is blocked. And both of them will let go of their carrier threads and wait. When the inner thread, virtual thread is ready, it's going to mount, execute it. Whenever the outer thread is ready to run, that's when it's going to execute by giving a carrier thread. So the virtual threads will block, but they will release their relative carrier threads.
Current virtual thread launches a parent thread, which then launches child virtual threads. And those virtual threads block, that carrier doesn't block.
Correct.
So the parent of that, the carrier never blocks.
Correct.
So how does it know to launch that test?
So keep in mind, your virtual threads always block. Your carrier threads are completely irrelevant at this point, because your carrier threads are just workers. And your carrier threads don't have any context of what they are running, because all they do is they say, you get mounted on me, I will do what you tell me to do. When you unmount, I'll go off and do something else. So the carrier threads have no context of what they run, because all the context lives in the virtual thread, not the carrier threads. Yep.
Thanks. Anyone? No.
We'll wait for Mary to come all the way here, then you can ask a question again.
Yeah. Exercise. Any question? Any question? No? I think we may have somebody from the YouTube, although I think you might have answered too, but let me
All right.
suddenly remember.
Sounds good. Thank
So
you.
Stan Tufi asked, what are best use cases to use Java virtual threads?
Yes.
Number one, CPU intensive compute. Number two, memory related tasks. And then three, IO intensive tasks.
Only three.
Only three.
Only three.
Only three.
That's extremely important to keep in mind. Do not use virtual threads if you are doing computation intensive jobs. Because if you're, and thanks for that question. So if you're doing computation intensive jobs, using virtual threads is actually detrimental because you're using a mechanism that involves mounting a thread and holding on to it for no good reason. That's the first problem. The second problem is, imagine the consequence of using computation intensive jobs. Let's step back. Very important question to talk about. So let's discuss that a little bit. So let's think about this for a minute. Suppose, right? So suppose you are doing computation, computationally intensive, jobs, right? So if you're doing computationally intensive jobs, what is something you need to be extremely aware of? And what you need to do is that number of threads that you have maximum, right? So you can say max number of threads is less than or equal to number of cores on your system. You should never exceed the number of cores on your system if you're doing computation intensive. Why? Because if you bump up the number of threads you are working with, they're going to start trashing your system. They're going to say, I need power. You are running. Give your space. I want to run. So they end up really dislodging each other, and you end up trashing. Your performance goes down. So you can do a very simple example of this. Keep creating threads, which are just doing computation, and the maximum performance you will get is when the number of threads equal to number of cores. You start increasing it, your performance actually goes down. So this is why you should not put computation intensive on virtual threads, because you're going to keep creating virtual threads for every single request. And when they all pop up, they're like, give me something to run. Give me a career thread to run. And your career thread is given, and they say, give me more, give me more, give me more. And now you have more threads running than the number of cores. Your performance goes down the drain. This is why you should not use virtual threads for computation intensive, because it makes what should be bounded into unbounded. And that's going to kill your performance, right? So you want to contain it. This is the reason why it's pretty interesting how they have done this. If you go down to this example, let's actually look at this code right here. If I were to ask, let me see if I can bring that here. If I were to ask right here, output, let's say, runtime, let's say runtime dot get runtime. So I want to take the runtime and say dot available processors. You will notice on my machine, it tells me that I have 16 cores, right? However, if I ask the question right here, if I say fork join pool, let's say pool dot common pool. So I'm going to ask for the common pool. Did you notice parallelism is 15? There's a reason why parallelism is 15. That's because number of cores I have is 16. Main is one of the threads. Main plus 15 is 16. That's why they're very careful limiting the common pool size to one less than the number of cores. If you turn this to virtual threads, you are telling them, you don't understand what I'm doing. I'm going to throw as many threads as I can. And their answer is good luck. Because now all your threads who have work to do are going to start kicking each other out. And you're going to end up trashing. So that's the reason why you shouldn't put computation intensive jobs on virtual threads, because you don't have ability to contain it to that number. So it's only for IO intensive. Very important question. Glad to hear that question, right? That's a reason for it. We can say don't do it, but it's important to understand why we shouldn't do it, because then we are a bit more cautious. We're not letting fear rule us. We have a reason why that doesn't make any sense to do. That's the reason.
Any more questions? No. No, I'm just curious. As you mentioned about it, because for AI, right? So their GPU. So how does it work? I'm just now you make me think because GPU we're also not supposed to be. It's more for computation.
Yes.
But how does it work then for GPU?
But often it's
versus
relieved from your
threads?
main CPU though,
Oh,
right? That's why it's an external computation.
Yeah.
But also typically
Yeah.
you might actually do it on a separate server
oh,
rather than being local,
Hmm.
right? Depends on your architecture, but typically you may have an external service that's doing all this work for you, and you're just making a request to that service to get the work done, rather than trying to have everything locally on the machines.
okay.
And even if you do locally on the machine, it could be a separate, execution engine rather than your own local processor.
Mm.
So your code is still relieved. It's waiting for your GPU to respond.
Oh,
Yeah.
okay, thank you. Okay, I guess no more question for now. Yeah, good. Oh, you have more. Okay. You make me.
Yeah, I just wanted to get a little bit more understanding regarding, the virtual thread, how it's implemented, because, the thread is at the operating system level and the virtual thread is at the JVM level.
Correct.
I was just curious, how, if you could provide a little bit more detail on how it's implemented.
In a very painful way. So this is why it took them 12 years to implement. I've been keeping an eye on this for, I'm going to say almost 8 years now. And about 8 years ago, I noticed that the sleep function worked with virtual threads, but files.lines didn't. And then files.lines worked, but URL calls didn't. So there was a gradual time when more and more functions started working. And essentially what they did was extremely painful. They went through every single JDK function. And inside those functions, they got code that says, who is calling me? If you're calling me from a virtual thread, do the work to unmount. And so this was a very painful, you can think of a change you have to make where you have to examine everything in your legacy system to make a change to it. That's what they had to do. It was an enormously painful and time-consuming job. Yeah, every function. And since you asked, as of today, if you are, this is a beautiful question. I love, that's why I love questions like this. As of today, if you do, remember, you have a lock interface. And if you have a reference to a lock interface, right? If you say mylock.lock, and then elsewhere you do mylock.unlock, for example, within try and finally all this good stuff. The minute you call lock, you will unmount. And the minute you call unlock, you will unmount and remount because you're releasing the lock and, so that the virtual threads will respond for a lock. So when you call a lock, you're waiting for the lock to be given, your virtual thread unmounts and waits. But again, this will change in the future. But instead of that, if you had said synchronize on, some stuff like so, if you are waiting for the synchronize to be available, your virtual thread will not unmount. They haven't implemented it yet because this requires a language level effort rather than a library level effort. So they haven't gotten to this yet. So that's one of the caveats. If you're using synchronize in your code, don't expect it to give you the benefits of virtual thread. But if you're using lock and unlock, you have the benefit of virtual thread. So to answer your question, that's why it's painstaking. This is not a boom, change that flag here and everything works. They had to go attack every single function to do this correctly.
So if I'm an architect, I would just tell or advise to stop using synchronize altogether.
That would have been an advice I gave even earlier than this, because I'm not a fan of synchronize myself, because I know exactly how to unit test code with lock. How in the world do you unit test a code with synchronize? So from the testability point of view, I signed off synchronize years ago. And if I want to do automated testing of my code, I've been using locks and unlocks than synchronize for a while now. So this is in sync, unintended, with what I would want to do, irrespective of this.
Okay. And we have another question from online audience. Aslam Suja asking, how does virtual thread work with reactive programming?
Awesome. So the first is, so to me, reactive programming means two separate things. One is I would do reactive programming for asynchronous calls. The other is I would do reactive programming for back pressure. If the reason I did reactive is for asynchronous, I have no reason to do it anymore, because I think virtual threads give a much better way to do it than reactive. But if I was doing reactive not for asynchronous or not only for asynchronous, but really for back pressure, I think that part still is useful. So I think that is the way to think about it. So asynchronous part is done better with virtual threads. So don't bother with the reactive programming for that purpose. But if you're saying, I've got a stream of data flowing in, I need to handle back pressure, I think there's still merit to doing reactive programming for that reason. So it depends on your use case.
Okay.
That's why I don't want to use the word reactive programming is dead. I don't believe so. Part of it is dead, but the other part, so it depends on what you're trying to do with it.
Good. Thank you.
Thank you.
All right, great.
Thanks for the question, Asam.
Aslam, thank you.
Yeah.
Anyone else have questions? No? Okay. All right, well, I guess, thank you.
Thank you.
Venkat.
Thank you.
Please- Yeah.
Thank you.
But now we will do the raffle. So if you have entered in, let me quickly get to that. Wait, where's my wheel of names? Okay, I just need to plug this in.
Oh, yes, please.
Yeah. Yeah. Thank you.
Come on over.
Okay, thank you. Just
Yeah.
a wheel of names, so. I guess this is. Take a little bit of time. Right. There, okay. Wheel of names. Did you enter your name?
No, I didn't.
Okay, yeah, I can enter it right now.
You.
The LIU, okay, Lou, yeah, okay. Okay, and so now we have Igor L, Alyssa, Tuan, Anish Roy, Greg, and William Burbett, and Aslam, Alexander, Nitin, and Lou. So, sure, what is your name? Alejandro, okay, okay. Alejandro, right? Yeah. Did I spell right? Yeah. Okay. You? Yeah, Jay. Oh, John. Yeah, okay. John, okay. But if you win, I'll need your email too. But okay. Anyone else? Yeah. Clint. KRN. KRN. KRITHN. I'm sorry. Yeah. Oh, the last one. This one? Like this. Okay, Kristen. Yeah. Okay. Yeah. And your name? Michael. Okay. All right. Okay. So now we have all of you on the wheel. Anybody else? And no one on the YouTube, right? Did anybody say? No. Okay. All right. You have to be present in order to win. So, okay. So we have two chances. So first spin. Okay, me too. Written. Okay, yeah, and I know written. Congrats. Okay.
I want to recount.
Oops. Where is it? Where's that? Okay, here we go. Now we have one more.
Pretty fancy, Mary.
Yeah, yeah. Yeah. Kristen, congrats, Kristen. Okay, great. And I need your email address, but I have Nitin. So, okay, so now it comes to an end, and I guess we can still hang out a little bit, although I think Venkat has to hurry to go back because you have an early flight out tomorrow, right? So, but I guess yeah, we can hang out with a little bit too. I think as long as it's okay with David as well. So yeah, just chat a little more if you like. There's still some pizzas if you want, and some soda. So yeah, so thank you so much again for joining us. And then for those of you who are going to go to, I think I'll see you tomorrow as well. So yeah, okay. So thank you, thank you, thank you. Thank you so much again, Venkat, and thank you. And thank you, Trey, for reporting, and Nitin too. Yeah, I forgot to thank Nitin too. Nitin took care of all the pizzas today, so thank you very much, and the soda. So thank you, and then thanks to this to Kotlin folks, to John and to Amanda too. So thank you. Yeah, thank you. Oh, thank you, Anita, for coming. Thank you all for joining. Thank you, thank you. So okay, great. Thank you, Venkat. Thank you so much. Yeah, really, that was fun. Yeah, yeah. Thank you, thank you, thank you, thank you for suggesting this. I know this is like usually we don't